Caustic stress corrosion cracking or caustic embrittlement damage mechanisms as a part of environment-assisted cracking. Description of caustic stress corrosion cracking or caustic embrittlement damage mechanisms based on API 571. A caustic embrittlement is a form of stress corrosion cracking characterized by surface-initiated cracks that occur in piping and equipment exposed to caustic, primarily adjacent to non-PWH'd welds. Here's a detailed description of caustic stress corrosion cracking or caustic embrittlement. Introduction. Caustic stress corrosion cracking or CSCC, commonly known as caustic embrittlement, is a form of environmentally assisted cracking that occurs in metallic components exposed to caustic, alkaline, environments under tensile stress. It is characterized by the initiation and propagation of cracks due to combined effects of mechanical stress and chemical environment, leading to material failure. Caustic stress corrosion cracking or caustic embrittlement in-depth explanation. Number 1 is fundamental mechanisms of caustic embrittlement. Chemical environment. The primary chemical agent involved is hydroxide ions, typically present in high concentrations in boiler water systems, especially in the vicinity of concentrated sodium hydroxide, potassium hydroxide, or other alkaline solutions. Stress factors, tensile stresses, whether residual, from manufacturing, welding, or cold working, or operational, pressure-induced, create conditions conducive to crack initiation. Crack initiation, surface or subsurface microstructural flaws or inclusions act as initiation sites, especially in areas of high tensile stress concentrations. Crack propagation. Once cracks form, the caustic environment facilitates crack growth via a process called caustic cracking, which is enhanced by localized chemical reactions at the crack tip, weakening the material along the crack front. Number 2 is detailed process of caustic embrittlement. Number A, buildup of alkaline concentration. In boiler systems, impurities such as sodium, potassium, or lithium compounds can concentrate in crevices, deposit areas, or corrosion products, raising local alkalinity. Water chemistry deviations, such as inadequate blowdown or pH control, increase the likelihood of high hydroxide ions concentration. Process of caustic embrittlement. Number B, residual and operational stresses. Components like boiler tubes, welds, or fittings often harbor residual stresses from manufacturing or welding. Operating pressures induce tensile stresses that, combined with residual stresses, exceed the material's resistance to crack initiation. Process of caustic embrittlement. Number C, crack initiation. Microcracks or flaws at the surface or within the material are exposed to the caustic environment. The high pH environment facilitates localized electrochemical reactions at flaws, weakening the material along grain boundaries or inclusions. Process of caustic embrittlement. Number D, crack growth. The caustic environment acts as an aggressive medium, promoting caustic cracking or embrittlement. The mechanism involves stress-assisted corrosion, where the chemical reactions at the crack tip cause material loss, further propagating the crack. Process of caustic embrittlement. Number E, intergranular or transgranular fracture. Cracks can propagate along grain boundaries, intergranular, or through grains, transgranular, depending on alloy composition, microstructure, and environment. Process of caustic embrittlement. Number F, final failure. As cracks grow, the structural integrity diminishes, leading to sudden or progressive failure under normal operating loads. Visual symptoms and damage manifestations of caustic embrittlement. It can be visualized as cracks, usually surface breaking or subsurface cracks aligned with stress directions. It can be visualized as metal loss, localized thinning or pitting due to corrosion. It's showing embrittlement zones, areas near welds or stress concentrators show signs of cracking, and it can be sudden failure. Often occurs without significant prior warning, especially in high-stress regions. Number 4 is prevention and control measures of caustic embrittlement. Number A, water chemistry management. Maintain proper pH levels and alkalinity control, use of high-quality feedwater and effective blowdown procedures. Avoid impurity buildup in crevices or deposit zones. Prevention and control. Number B, stress management. Reduce residual stresses via stress relief heat treatments. Design components to minimize stress concentrations. Regular inspection and removal of stress risers. Prevention and control. Number C, material selection. Use of resistant alloys or materials less susceptible to caustic cracking. Avoiding materials prone to embrittlement in alkaline environments. Prevention and control. Number D, protective coatings and surface treatments, applying corrosion-resistant coatings to prevent exposure, use of surface treatments to reduce surface flaws. Prevention and control. Number E, monitoring and inspection, regular non-destructive testing or NDT such as ultrasonic testing, dye penetrant, or magnetic particle inspection to detect early cracks. Monitoring water chemistry parameters continuously. Caustic stress corrosion cracking, caustic embrittlement, is a destructive process that occurs when tensile stresses and high alkalinity environments synergistically cause crack initiation and propagation in susceptible metals, particularly in boiler and pressure vessel systems. It is characterized by intergranular or transgranular cracking, often leading to sudden failure if not detected early. Effective prevention involves controlling water chemistry, reducing residual stresses, selecting appropriate materials, and implementing rigorous inspection regimes. Understanding the detailed mechanisms enables engineers and maintenance personnel to design, operate, and maintain systems that are resilient against this form of environmentally assisted cracking. Caustic stress corrosion cracking or caustic embrittlement based on API 571 will affected carbon steel, low alloy steels and 300 series SS are susceptible. Nickel base alloys are more resistant. Here's a comprehensive and detailed explanation of materials affected by caustic stress corrosion cracking or caustic embrittlement. Overview: Caustic stress corrosion cracking or CSCC, also known as caustic embrittlement, predominantly affects specific metals and alloys that are susceptible to chemical attack in high pH, alkaline, environments under tensile stress. Understanding which materials are vulnerable is crucial for selecting appropriate materials for high-risk environments, especially in power plants, boilers, and chemical processing facilities. Materials affected by caustic stress corrosion cracking or caustic embrittlement damage includes: number 1 is primary susceptible materials, number A, carbon steels and low alloy steels. These are the most susceptible materials to caustic embrittlement due to their microstructure and chemical composition. Carbon steels contain primarily iron and carbon, with minimal alloying elements. They are widely used in boiler components, piping, and pressure vessels. When operating in environments with high alkalinity and residual tensile stresses, cracks tend to initiate and propagate along grain boundaries, especially along microstructural. The primary susceptible materials. Number B, welded steels and heat-affected zones. Welded joints and HAZ are particularly vulnerable because welding introduces residual stresses and microstructural changes. Here's detail of welded steels and heat-affected zones affected. CSCC, residual stresses from welding act as stress concentrators. The microstructure in HAZ can be more susceptible due to grain growth or microvoids. Weld imperfections or inclusions can serve as crack initiation sites. Number 2 of materials affected by caustic stress corrosion cracking or caustic embrittlement damage is susceptible alloy types, includes: number A, cast steels with certain microstructures and compositions are prone to caustic cracking. Details of cast steels. Material affected by CSCC, especially susceptible when casting defects or microvoids exist. The coarse microstructure can facilitate crack propagation along grain boundaries. Number B, low to medium alloy steels. Alloys such as low alloy steels may have some resistance but can still be affected under severe conditions. Details of low to medium alloy steels. Material affected by CSCC, alloying elements like chromium or nickel may improve resistance but do not eliminate susceptibility entirely. Number 3 of materials affected by caustic stress corrosion cracking or caustic embrittlement damage is materials generally less susceptible, includes: number A, austenitic stainless steels, generally resistant to caustic embrittlement. Details of austenitic stainless steels. Material affected by CSCC, austenitic stainless steels, such as 304, 316, have high chromium and nickel content, which form a protective oxide layer. They are less susceptible because their microstructure is stable in high pH environments and less prone to intergranular attack. However, under certain conditions, such as high residual stresses, very high alkalinity, or specific microstructural features, they may still be at risk. Number B, nickel-based alloys. Highly resistant to caustic cracking, details of nickel-based alloys. Material affected by CSCC. Alloys like Inconel or Monel exhibit excellent chemical stability in alkaline environments and high-temperature conditions, used in high-stress, high-temperature environments where caustic embrittlement is a concern. Number 4 of materials affected by caustic stress. Corrosion, cracking or caustic embrittlement damage is factors influencing material susceptibility. Number A, microstructure. Fine-grained structures tend to be more resistant than coarse-grained microstructures. Presence of microvoids, inclusions, or grain boundary precipitates increases susceptibility. Number B of factors influencing material susceptibility. Caustic embrittlement is residual and operating stresses. Components with residual tensile stresses from welding, forming, or thermal cycling are more vulnerable. Number C, chemical composition. Higher carbon content increases susceptibility. Presence of impurities or inclusions can act as crack initiation sites. Number D of factors influencing material susceptibility. Caustic embrittlement is temperature. Elevated temperatures, above 130 degrees Celsius or 266 degrees Fahrenheit, accelerate embrittlement mechanisms. In summary, carbon steels and low-alloy steels are most vulnerable to caustic stress. Corrosion, cracking, caustic embrittlement. Their susceptibility is primarily due to their microstructure, residual stresses, and chemical composition. Welded components and heat-affected zones are particularly at risk because of residual stresses and microstructural heterogeneity. Conversely, austenitic stainless steels and nickel alloys generally have high resistance, making them suitable choices where caustic environments are present. Proper material selection, stress management, water chemistry control, and regular inspection are vital to prevent or mitigate caustic embrittlement in susceptible materials. Caustic stress, corrosion, cracking, caustic embrittlement damage. Critical factors based on API 571. Number A, susceptibility to caustic embrittlement in caustic soda and caustic potash solutions is a function of caustic strength, metal temperature, and stress levels. Number B, increasing caustic concentration and increasing temperatures increase the likelihood and severity of cracking. Conditions likely to result in cracking have been established through plant experience and are presented in Figure 4-146, recommended operating limits for carbon steel in caustic service. Number C, cracking can occur at low caustic levels if a concentrating mechanism is present. In such cases, caustic concentrations of 50 to 100 ppm are sufficient to cause cracking. Number D, stresses that promote cracking can be residual that result from welding or from cold working, such as bending and forming, as well as applied stresses. See Figure 4-147. Cracking initiating on the inside surface of a non-stress relieved carbon steel heat exchanger. Bend after 8 years in 15% to 20% caustic service at 140 degrees Fahrenheit to 240 degrees Fahrenheit or 60 degrees Celsius to 115 degrees Celsius. See Figure 4-148. Photomicrograph of a crack in the tube shown in Figure 4-147. Number E, it is generally accepted that stresses approaching yield are required for SCC so that thermal stress relief or PWHT is effective in preventing caustic SCC. See Figure 4-146, recommended operating limits for carbon steel in caustic service. Although failures have occurred at stresses that are low relative to yield, they are considered more rare. See Figure 4-149, cracking at a boiler tube sheet due to caustic concentrating between the tube and the tube sheet. See Figure 4-150, photomicrograph of a crack in the tube sheet shown in Figure 4-149. Number F, crack propagation rates increase dramatically with temperature and can sometimes grow through wall in a matter of hours or days during temperature excursions, especially if conditions promote caustic concentration. Concentration can occur as a result of alternating wet and dry conditions, localized hot spots or high-temperature steam out. Number G, special care must be taken with steam tracing design and steam out of non-PWHT'd carbon steel piping and equipment. See Figure 4-151. Photomicrograph of caustic cracking initiating on the ID of a carbon steel socket weld in a non-PWHT'd piping in a suction drum downstream of a caustic scrubber. Unetched. See Figure 4-152, Figure 4-151 in the etched condition. Here's a comprehensive and detailed explanation of the critical factors influencing caustic stress. Corrosion, cracking, Caustic embrittlement. Caustic embrittlement results from the complex interplay of environmental, material, and operational factors. Understanding these critical factors is essential for predicting, preventing, and controlling this form of damage. Here's a details of critical factors of caustic embrittlement. Number 1 is chemical environment factors. Factor number A is alkalinity or high pH or high concentration of hydroxide ions. Alkalinity. Elevated concentrations of hydroxide ions increase the likelihood of caustic cracking. Details of alkalinity. Localized high alkalinity often occurs in crevices, deposit areas, or regions with impurity accumulation. Excessive alkalinity facilitates localized electrochemical reactions at crack tips, weakening grain boundaries. Number B of chemical environment factors is impurities and deposits. Presence of impurities, such as sodium, potassium, lithium, in water can concentrate in crevices or deposits. Details of impurities and deposits. These impurities raise local pH levels, creating ideal conditions for caustic cracking. Deposits, scale, sludge, can trap impurities, sustaining high alkalinity locally. Number C of chemical environment factors is water chemistry control. Poor water chemistry management leads to increased susceptibility. Details of water chemistry control. Inadequate blowdown, pH control, or impurity removal causes alkalinity buildup. Maintaining proper water chemistry is essential to reduce caustic embrittlement risk. Number 2 of critical factors of caustic stress corrosion cracking or caustic embrittlement is mechanical and stress factors, includes, number A, residual stresses. Description: stresses remaining in materials from manufacturing, welding, or thermal cycles. Details of residual stresses. Residual tensile stresses are critical for crack initiation. Welding induces localized residual stresses and microstructural changes that promote cracking. Number B of mechanical and stress factors is operating stresses. Description: external or internal stresses due to pressure, temperature, or operational loads. Details of operating stresses. High internal pressure in boilers or pipes causes tensile stresses. Thermal stresses during startup/shutdown cycles contribute to stress levels. Number C of mechanical and stress factors is stress concentrators. Description: geometric features such as welds, abrupt changes in cross-section, corrosion pits, or microvoids. Details of stress concentrators. These act as initiation sites for cracks. Areas with stress concentration are more vulnerable even under normal operating stresses. Material factors of caustic embrittlement includes, number A, microstructure and composition. Description: microstructural features influence susceptibility. Details of microstructure and composition. Critical factors includes, coarse-grained microstructures and grain boundary precipitates facilitate crack initiation. High carbon content and certain inclusions increase vulnerability. Microvoids and microcracks serve as initiation points. Number B of material factors of caustic embrittlement is material microhardness and toughness. Description: lower toughness and microhardness may predispose materials to cracking. Details of material microhardness and toughness. Materials with lower ductility are more prone to brittle-like cracking under stress. Number C of material factors of caustic embrittlement is microstructural changes from welding. Description: welding modifies the microstructure and induces residual stresses. Details of microstructural changes from welding. Heat-affected zones often have altered grain structures that are more susceptible. Critical factors. Number 4 is environmental and operational factors, includes, temperature. Elevated temperatures accelerate chemical reactions and embrittlement processes. Temperatures above approximately 130 degrees Celsius or 266 degrees Fahrenheit increase susceptibility. Higher temperatures also reduce material toughness. Environmental and operational factors. Number B is duration of exposure. Longer exposure times allow cracks to initiate and propagate. Cumulative effects over operational cycles increase damage likelihood. Environmental and operational factors. Number C is presence of crevices or deposit areas. Areas where water chemistry cannot be easily controlled. Crevices, deposit layers, or areas with poor circulation trap impurities and concentrate alkalinity. Additional of critical factors of caustic stress corrosion cracking or caustic embrittlement. Number A, microstructural heterogeneities. Variations in microstructure, such as grain size and inclusions. Heterogeneities serve as nucleation sites for crack initiation. Additional factor number B, surface conditions, surface roughness, corrosion pits, or flaws. Surface imperfections act as stress concentrators and crack initiation sites. Additional factor number C, component design, design features influencing flow and chemical distribution. Poorly designed systems may promote crevice formation and localized chemical environments. Interdependence, these factors often act synergistically. For example, residual stresses combined with high alkalinity in crevices significantly increase the risk. Control strategies. To mitigate caustic embrittlement, it is essential to manage water chemistry, minimize residual stresses, avoid design features that promote crevice formation, and select resistant materials. Caustic stress corrosion cracking or caustic embrittlement damage affected units or equipment based on API 571. Number A, caustic embrittlement is often found in piping and equipment that handles caustic, including H2S and mercaptan removal units, as well as equipment that uses caustic for neutralization in sulfuric acid alkylation units and HF alkylation units. Caustic is sometimes injected into the feed to the crude tower for chloride control. Number B, failures have occurred in improperly heat-traced piping or equipment as well as heating coils and other heat transfer equipment. Number C, caustic embrittlement may occur in equipment as a result of steam cleaning after being in caustic service. Number D, traces of caustic can become concentrated in BFW and can result in caustic embrittlement of boiler tubes that alternate between wet and dry conditions due to overfiring. Here's a detailed explanation of the units and equipment affected by caustic stress corrosion cracking or caustic embrittlement. Caustic embrittlement predominantly impacts equipment and units operating in high-temperature, high-alkalinity environments, especially within thermal power plants, chemical processing facilities, and other industrial systems involving boiler and piping components. Units and equipment affected by caustic embrittlement. Number 1 is boilers and boiler components, includes, number A, boiler shells and pressure parts. The boiler shell and pressure vessels are exposed to high-temperature water or steam, making them highly susceptible. Caustic cracking can initiate along welds, microvoids, or microcracks in the shell or tube sheets. Corrosion and cracking often occur in crevice-like regions where deposits or scale concentrate alkalinity. Number B, water walls and refractory line sections. The water walls, furnace walls with water tubes, are exposed to hot, high alkaline water, especially in areas with poor water circulation or deposit buildup. Microcracks can develop along welds or in microstructural weaknesses caused by thermal stresses. Boiler component number C, economizer and superheater tubes. These tubes operate at high temperatures and are exposed to corrosive environments, especially when deposit buildup occurs. Cracks can propagate along welds or at locations with residual stress. Next, number 2 of units and equipment affected by caustic embrittlement is piping systems, includes, number A, high-pressure steam and water pipelines. Piping conveying superheated steam or hot water can develop cracks, especially at weld joints, bends, or constrictions. Areas with crevice-like features or deposits are more vulnerable. Piping systems number B, feed water and condensate lines. These lines often contain high pH water and are susceptible to caustic attack at welds or microvoids. Microcracking may occur during thermal cycling. Number 3 of units and equipment affected by caustic embrittlement is welded joints and heat-affected zones. Welds are common sites for crack initiation due to residual stresses and microstructural changes. The HAZ experiences grain growth and microstructural heterogeneity, making it vulnerable. Cracks often propagate along grain boundaries in the weld metal or HAZ. Number 4 of units and equipment affected by caustic embrittlement is valves and fittings. Valves, especially those with welds or microstructural discontinuities, are at risk. Cracking can occur at sealing surfaces or in the body due to residual stresses and high-temperature caustic environment. Number 5 of units and equipment affected by caustic embrittlement is supercritical and ultra-supercritical units. These advanced units operate at very high pressures and temperatures. The associated components such as turbine blades, casings, and boiler pressure parts can be affected, especially if water chemistry is not properly controlled. Number 6 of units and equipment affected by caustic embrittlement is condensers and heat exchangers. Although less common, areas with high residual stresses or microstructural heterogeneity can suffer from caustic cracking if exposed to high alkaline environments. Number 7 of units and equipment affected by caustic embrittlement is chemical reactors and processing units. In chemical industry, equipment handling high pH chemicals or operating at high temperatures and pressures may be vulnerable. Welded vessels, piping, and reactors are susceptible if operating conditions favor caustic embrittlement. Additional insights of caustic stress corrosion cracking or caustic embrittlement. Location-specific vulnerability. Caustic embrittlement tends to occur inside crevices or deposit areas where high pH conditions develop locally. Welded areas are high-risk zones because of residual stresses and microstructural changes. Operational conditions such as frequent thermal cycling, poor water chemistry control, and high residual stress states exacerbate the damage potential. Appearance or morphology of caustic stress corrosion cracking or caustic embrittlement based on API 571. Number A. Caustic stress corrosion cracking typically propagates parallel to the weld and adjacent base metal but can also occur in the weld deposit or heat-affected zones. Number B. The pattern of cracking observed on the steel surface is sometimes described as a spider web of small cracks which often initiate at or interconnect with weld-related flaws that serve as local stress. Razors. Number C. Cracks can be confirmed through metallographic examination as surface-breaking flaws that are predominantly intergranular. The cracking typically occurs in as-welded carbon steel fabrications as a network of very fine, oxide-filled cracks. Number D. Cracking in 300 series SS is typically transgranular and is very difficult to distinguish from chloride stress corrosion cracking. See Figure 4-153. Stainless steel expansion bellows from a steam-driven turbine previously subjected to a caustic carryover upset condition. Here's a detailed explanation of the appearance and morphology of caustic stress corrosion cracking. Caustic embrittlement, damage. Caustic embrittlement typically manifests as distinct, characteristic features on affected metallic components. Understanding its morphology helps in identifying and diagnosing the damage. Appearance and morphology of caustic stress corrosion cracking or caustic embrittlement. Number 1 is general morphological features, includes, number A, cracks, often intergranular, along grain boundaries, but can also be transgranular depending on severity. Appearance of cracks, fine, hairline cracks initially, which may grow over time. Cracks are usually elongated, parallel to the surface, and rough in cross-section. They often propagate along grain boundaries due to localized chemical attack and stress concentration. Cracks may be wavy or straight depending on the microstructure and stress distribution. Feature number B, microvoids and microcracks. Initial stages, microvoids develop at grain boundaries or around inclusions. These coalesce to form microcracks. Feature number C, crack features. Step-like features. Cracks may show step-like or faceted morphology along grain boundaries. This results from the intergranular nature of the propagation. Appearance and morphology of caustic embrittlement. Number 2 is surface features, includes, number A, fracture surface morphology or brittle appearance. The fracture surface tends to be smooth and shiny, brittle fracture, or dull and granular depending on the microstructure. Brittle fracture surfaces often show cleavage facets or intergranular fracture features. Surface features. Number B, corrosion pits and deposits. Areas with scale buildup or residues of deposits often correlate with crack initiation sites. Pitting corrosion may be observed in conjunction with cracking. Surface features. Number C, crevice and deposit regions or localized damage. Crack initiation and propagation are often localized in crevice or deposit zones, where high alkalinity concentrates. Appearance and morphology of caustic embrittlement. Number 3 is microstructural features, includes, number A, grain boundary attack appears as, micrographs reveal intergranular cracks along grain boundaries. Grain boundaries may appear widened or etched due to corrosion. Number B, inclusion and secondary phase attack. Corrosion may be concentrated around inclusions or microconstituents, leading to microvoid formation. Appearance and morphology of caustic embrittlement. Number 4 is crack propagation morphology, includes, number A, intergranular propagation. Cracks tend to follow grain boundaries, often resulting in intergranular fracture. The crack path can be irregular, wavy, or step-like. Grain boundaries may appear widened or etched due to corrosion. Number B, transgranular propagation. Less common but can occur in severe cases, with cracks crossing grains and exhibiting cleavage facets. The intergranular morphology is a hallmark of caustic embrittlement. The fracture surfaces are often brittle, with features characteristic of low ductility failure. Crack initiation typically occurs in crevice zones, deposit areas, or welds, then propagates along grain boundaries. Caustic embrittlement prevention and mitigation based on API 571, number A, cracking can be effectively prevented by means of a stress-relieving heat treatment, such as PWHT. A heat treatment at 1150 degrees Fahrenheit or 621 degrees Celsius is considered an effective stress-relieving heat treatment for carbon steel. The same requirement applies to repair welds and to internal and external attachment welds. Number B, 300 series SS offer little advantage in resistance to cracking over CS. Number C, nickel-base alloys are more resistant to cracking and may be required at higher temperatures and/or caustic concentrations. Number D, steam out of non-PWHT'd carbon steel piping and equipment should be avoided. Equipment should be water washed before steam out. Where steam out is required, only low-pressure steam should be used for short periods of time to minimize exposure. Number E, proper design and operation of the injection system is required to ensure that caustic is properly dispersed before entering the high-temperature crude preheat system. Here's a comprehensive, detailed explanation of prevention and mitigation strategies for caustic stress corrosion cracking or caustic embrittlement. Caustic embrittlement is a form of environmentally assisted cracking that occurs when high alkalinity, caustic soda, NaOH, in high-temperature water interacts with residual or applied stresses in susceptible metals, especially in boiler and high-pressure systems. Preventing and mitigating this damage involves controlling water chemistry, design considerations, material selection, and operational practices. Here is a comprehensive, detailed explanation of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement. Includes, number 1, water chemistry control. Number A, maintain low alkali concentration. Prevent high local pH conditions that promote caustic buildup. Methods can be used to maintain low alkali concentration, includes, use high-quality, well-conditioned feedwater with controlled pH, add phosphate treatments such as sodium phosphate to precipitate and remove free caustic, use ammonia or hydrazine to adjust pH to acceptable levels, ensuring it remains below critical thresholds. Number B of water chemistry control is use of proper oxygen control. Its objective is to minimize corrosion products that can deposit and concentrate alkalinity. Methods in use of proper oxygen control includes, maintain adequate oxygen levels, or deaerate, to reduce corrosion and oxygen-related deposits, use oxygen scavengers to remove residual oxygen. Number C of water chemistry control is prevent deposit formation. Its objective is avoid deposits that create crevices or localized high pH zones. Methods to prevent deposit formation includes, regular blowdown to remove accumulated sludge and scale, use of filtration and softening to prevent mineral deposits. Number D of water chemistry control is control pH within acceptable limits, keep boiler water pH in an optimal range, typically 9.8 to 10.5 for high-pressure boilers, avoiding excessive alkalinity that can lead to caustic buildup. Number 2 of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement is design and material selection. Number A, use of resistant materials. Objective of using resistant materials is to reduce susceptibility to caustic embrittlement, for example, austenitic stainless steels, nickel-based alloys, or other corrosion-resistant materials. Avoid high-strength ferritic steels or materials known to be susceptible to caustic cracking. Design and material selection. Number B is minimize stress concentrations. Design considerations, use smooth welds and transitions, avoid abrupt changes in cross-sectional areas, incorporate stress relief features post-welding. Design and material selection. Number C is avoid use of hard, brittle materials in critical areas, use materials with good ductility and toughness for welds and high-stress zones. Number 3 of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement is operational practices, includes, number A, stress reduction or stress relief, perform post-weld heat treatment, PWHT, where applicable, use controlled thermal cycling to reduce residual stresses, limit startup and shutdown stresses through proper procedures. Operational practices. Number B is maintain proper operating conditions, Keep temperature and pressure within design limits to prevent excessive stress or temperature gradients. Avoid rapid temperature changes which induce thermal stresses. Operational practices. Number C is regular inspection and monitoring. Use non-destructive testing, such as ultrasonic, dye-penetrant, visual inspections, to detect early cracks. Employ corrosion monitoring techniques, such as coupons, pH probes, deposit analysis. Number 4 of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement is chemical treatments and additives, includes, number A, chemical inhibitors, use corrosion inhibitors formulated to reduce caustic activity or passivate susceptible surfaces. Number B, pH adjustment agents, use appropriate chemicals to maintain a stable, controlled pH within safe limits. Number C, deposit control agents, use dispersants or anti-scale agents to prevent deposit buildup that can promote localized high pH zones. Number 5 of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement is maintenance and inspection, includes, number A, regular cleaning and descaling, remove scale, sludge, and deposits to prevent crevice formation, use chemical cleaning agents compatible with boiler materials. Number B, to maintenance and inspection for crack detection, employ boiler tube inspections, visual examinations, and advanced techniques such as replica testing or penetrant testing to detect early signs of cracking. Number C, maintenance and inspection for repair and replacement, promptly repair or replace cracked or compromised components to prevent catastrophic failure. Number 5 of prevention and mitigation of caustic stress corrosion cracking or caustic embrittlement is operational strategies in high-risk areas, includes, number A, control crevice and crevice-like environments, design welds and joints to minimize crevice formation, avoid stagnant zones where high alkalinity can concentrate. Number B, use of protective coatings or linings. Apply suitable coatings to prevent direct contact of susceptible metals with caustic solutions. Prevention of caustic embrittlement requires an integrated approach combining water chemistry control, design considerations, material selection, and operational practices. Maintaining optimal conditions and vigilant inspection are essential to prevent the initiation and propagation of cracks, thus ensuring the integrity and safety of high-temperature, high-pressure equipment. Caustic stress corrosion cracking or caustic embrittlement prevention and mitigation based on API 571, number A. Although cracks may be seen visually, crack detection is best performed with WFMT-EC, RT, or ACFM techniques. Surface preparation by grit blasting, high-pressure water blasting or other methods is usually required. Number B, PT may not be effective for finding tight, scale-filled cracks and should not be used as the only means of detection. Number C, fine cracks may be difficult to find with RT. Number D, crack depths can be measured with a suitable UT technique including external SWUT. Number E, AET can be used for monitoring crack growth and locating growing cracks. Here's a detailed explanation of the inspection and monitoring methods used to detect caustic stress corrosion cracking or caustic embrittlement damage. Caustic embrittlement manifests as intergranular or transgranular cracks, often brittle in nature. Early detection is critical to prevent catastrophic failure. The inspection methods focus on identifying cracks, corrosion products, deposits, and material degradation associated with caustic cracking. Here's a detailed overview of inspection and monitoring methods for detecting caustic stress corrosion cracking or caustic embrittlement. Includes, number 1 is visual inspection. It is purposed to identify surface indications such as cracks, corrosion deposits, discoloration, or surface roughness. The first method in use for visual inspection is direct visual inspection, performed with adequate lighting and magnification. Focus on areas prone to stress and deposit accumulation, like welds, bends, or crevices. And the second visual inspection method is remote visual inspection or RV, use of borescopes or videoscopes for internal surfaces, especially inside boilers or pipes. Indicators damage when performing visual inspection, includes, cracks, fine, hairline, intergranular cracks often visible as lines or discoloration, deposits, scale, sludge, or caustic deposits indicating high alkalinity zones, corrosion features, pitting or roughness near welds or crevices. Inspection and monitoring methods for detecting caustic embrittlement. Number 2 is dye penetrant testing or DPT. It is purposed to detect surface breaking cracks, especially fine intergranular cracks that are visible under magnification. Dye penetrant testing or DPT procedure includes clean the surface thoroughly, apply penetrating dye, allow adequate dwell time, remove excess dye and apply a developer. Cracks filled with dye will appear as colored indications. The advantages of dye penetrant testing are sensitive to fine cracks and useful for surface crack detection on accessible areas, and the limitations of dye penetrant testing are, it cannot detect subsurface cracks, and the surface to be inspected must be clean and smooth. Inspection and monitoring methods for detecting caustic embrittlement. Number 3 is ultrasonic testing or UT. UT purpose to detect internal cracks or flaws that are not visible on the surface. Here's a few UT techniques can be used to detect caustic embrittlement. Includes Polseco method, suitable for detecting cracks, especially in thick components. Phased array ultrasonics provides detailed imaging of internal structures. Time of flight diffraction or TOFD for precise crack length measurement. Ultrasonic testing applied to scan welds, thick sections, or areas with high residual stresses. And detect internal intergranular or transgranular cracks. The limitations of ultrasonic testing requires skilled operators, may be less sensitive for very small cracks. Inspection and monitoring methods for detecting caustic embrittlement. Number 4 is replicating or replica techniques. It is purposed to examine surface micro cracks without damaging the component. Here's procedure of replica techniques. Apply a polymethyl methacrylate or PMMA or nylon replica material onto the surface. After curing, remove the replica. Examine under a microscope, optical or SEM, for crack morphology and density. The advantages of replica techniques: it allows detailed microstructural analysis, suitable for monitoring crack growth over time. Inspection and monitoring methods for detecting caustic embrittlement. Number 5 is microstructural and metallographic examination. It is purposed to analyze crack initiation sites and propagation mechanisms at the microscopic level. Microstructural and metallographic technique procedures: prepare metallographic samples, use optical microscopy or scanning electron microscopy, SEM, to investigate crack paths, grain boundary attack, and corrosion features. This microstructural and metallographic examination applied to confirm intergranular nature of cracks and to identify corrosion deposits and microvoids. Inspection and monitoring methods for detecting caustic embrittlement. Number 6 is deposit and corrosion product analysis. It is purposed to identify deposits that may have facilitated crack initiation. Methods O detect deposit and corrosion includes chemical analysis of deposits via spectroscopy, visual examination for scale or sludge. And the implication is to help correlate deposit zones with crack locations. Inspection and monitoring methods for detecting caustic embrittlement. Number 7 is monitoring techniques, includes, number A, corrosion coupons and probes. Place metal coupons in service to monitor corrosion rates and crack-related degradation. Use pH probes and electrochemical sensors to monitor water chemistry, especially pH and alkalinity. Monitoring techniques. Number B, acoustic emission monitoring, detects high-frequency stress waves generated by crack initiation or growth, suitable for real-time monitoring of active cracking. Monitoring techniques. Number C, stress and strain monitoring, use strain gauges or stress meters to identify areas under high stress that are susceptible to cracking. Monitoring techniques. Number D, regular inspection schedules, implement routine inspections based on risk assessment, use a combination of visual, ultrasonic, and dye penetrant testing. Early detection of caustic stress corrosion cracking relies on combining multiple methods. Routine inspections and non-destructive testing are critical for ongoing maintenance. Microstructural analysis provides insight into crack mechanisms and guides preventive measures. Monitoring of water chemistry complements physical inspections, helping prevent crack initiation. Thank you.